Today, we're really going to start talking about forces. So far, we've mostly talked about things moving, but not really given a reason for why they move or accelerate. And really, what we're going to get into today is forces, which sort of is the cause behind all of that. It's why things move, why things change their movement, and also kind of why things sit still sometimes. And to get started with that, we're going to introduce you guys to Sir Isaac Newton a little bit, because a lot of what we're talking about is what we call Newtonian mechanics. It really came from Isaac Newton. So say hello to Isaac Newton. Isaac says hello to you. Isaac Newton was born in 1642 on Christmas Day. This was the same year that Galileo died. And Isaac Newton was a really tiny baby. He was very premature and not expected to live. Fortunately for us, he did. He lived, grew up with his mother part of the time and with his grandmother part of the time, and then back with his mother. And at age 13, went away to grammar school and lived in town with the local apothecary. And he was expected to come back home at 17 and be a farmer. Luckily for us, he was a lousy farmer, and it's been said that he was an utter failure as a farmer. His mother's brother convinced his mother that he should instead go to school and study, that would be a much better sort of route for him. And so he left for Trinity College in Cambridge in 1661. He paid his way through college. He waited tables. He cleaned up for faculty and wealthier students, and eventually was elected as a scholar, which gave him a 4-year scholarship, paid for his tuition for 4 years. And things were going really well until the plague actually reached the Cambridge area in 1665. He had to return home, and he spent the time when he was at home really concentrating on studying math and physics, and came back in a much better spot. He returned in 1667, began to work on alchemy, and then scholar Mercator published a book talking about sort of mathematical methods. And Newton wrote this response to that, talking about his much broader results. He had a mentor named Isaac Barrow, who had just been sort of appointed to this prestigious professorship, Lucasian professorship. And Barrow passed on Newton's work. It got a lot of acclaim, and then Barrow actually resigned his professorship so Newton could have the job. And an interesting twist with this, at that time, to sort of have that job at Trinity College, the person in that role had to agree to take holy orders, to be a fellow of Trinity College, holy orders within the Church of England. And Newton wasn't really comfortable with this. He wasn't able to accept the current beliefs, but the church actually made a royal decree. Well, King Charles II made a royal decree that excused him from needing to take the holy orders, and in fact excused anyone into the future from being required to take the holy orders. They were allowed to, just not required to. One of the most famous, sort of more recent people to hold this professorship was actually Stephen Hawking. So there's Isaac Newton at Trinity College in Cambridge. His first major public scientific achievement was that he built a reflecting telescope. He didn't just design it, he ground the glass and did everything to build it. And then in 1686, he published Principia, which is really a foundational work for all that we know about physics today. It was where he first talked a lot about universal gravitation, and is really a basis for a lot of our current understanding of physics. That's a little bit of history, but I think it's great to know a little bit about where all of this came from. Because again, much of our understanding of how and why objects move is really based on concepts that arose from Newton. You hear it in popular culture sometime about Newton having the apple fall on his head, and that being part of his understanding of gravitation, and he's really sort of the father of a lot of what we understand with physics. So, back to forces. We've talked a lot about acceleration. Acceleration is a change in velocity, and acceleration is associated with a force, a push or a pull. I don't know if this has happened to you when you've thought about acceleration in thinking through the problems, but a lot of times you can sort of think of it as being if something is moving to the right, but slowing down, it's like it's being pulled to the left. And kind of intuitively, we know that for something to change velocity, it requires a force. So what are forces? Well, forces come in many types and sizes. We have forces that we call applied forces, which are when you push on something. We have spring forces, we have tension forces, we have electrical forces, magnetic forces, friction forces, lots of different types, and they come in all kinds of sizes, from the very, very tiny to the very, very huge. One term we use to sort of group them is that forces can be contact or non-contact. When this man on the left is running along with his jogging stroller, he is contacting the stroller right here and pushing. So that would be an applied contact force because he's actually touching the object on which he's exerting the force. We have this skydiver right here. We know that the Earth is exerting a force of gravity on the skydiver, but the Earth isn't touching the skydiver. So gravity is often a non-contact force. The two objects do not need to be touching for gravity to act. We'll also find that electric forces are non-contact, and what you've probably seen is magnetic forces are non-contact. A magnet can affect an object even when they are not in contact. Regardless of whether a force is contact or non-contact, forces always come from the interaction of two bodies. You cannot have a force that only involves one body. If we think about the skydiver, we might only really see the skydiver, but that force of gravity comes from an interaction of the skydiver and the Earth. For the man pushing the stroller, the force that's moving the stroller forward comes from the man interacting with the stroller. And we always have to have this interaction of two bodies to have a force. This brings us to Newton's first law, now that we have a sense of what forces are. And Newton's first law is very commonly misquoted, but it's something that you've probably heard of before. So Newton's first law says that when no net force acts on a body, it moves with a constant velocity. You'll frequently hear it stated as a body in motion tends to stay in motion, a body at rest tends to stay at rest. And that's mostly true, but Newton's first law is a bit more rigorous than that. So no net force means that if we add all the forces acting on the body, the sum of them is 0. This doesn't mean there are no forces acting on the body. It just means that the sum of the forces is 0. And when we talk about the sum of the forces, we're going to talk about a vector sum. We also say that it moves with a constant velocity. This does not mean that it stays at rest necessarily. If it is at rest, then a constant velocity obviously is staying at rest. But if it is moving, it remains moving in a straight line and at the same speed, because that's what would be a constant velocity. So the common phrasing of Newton's first law as a body at rest tends to stay at rest and a body in motion tends to stay in motion could be more accurately rephrased as a body at rest tends to stay at rest and a body in motion tends to stay in motion in the same direction and at the same speed unless acted upon by an unbalanced force. When we say unbalanced force, we mean that there's not another force with the same magnitude in the opposite direction, so that the net force is equal to 0. So let's think about this in a few situations. Say I go to the front door of my house, which is locked, and I push on it. I can push as hard as I want, and the door is not going to move. Because when I push on the door, the lock and the frame of the door push on the door in the other direction, so there's no net force on the door, and it doesn't accelerate. What if I slide a hockey puck across the ice, and we'll say the ice has just been sort of zambonied, it is perfectly smooth, and when I slide that hockey puck, it's going to just keep going in a straight line at the same speed until it hits the wall or something like that. And when it hits the wall exerts a force on it and produces an acceleration. It changes that velocity. So as long as it's sliding across the ice there's no net force acting on my hockey puck. And it slides with a constant velocity. I say no net force because gravity is still acting on the hockey puck and the ice is still holding the hockey puck up, but the sum of those two forces are zero. Sum of the forces is zero. I apologize for my grammar. What if I roll a ball across the floor? If it's a nice smooth floor, this works just like the hockey puck. My ball will keep rolling forever as long as the floor is flat and is very, very smooth until some other force acts upon it. What about if I'm driving to work one morning and I'm running a little bit late and I've got my coffee sitting up on the dashboard and I turn really sharply to the left? My car is going to turn, but my coffee isn't going to turn. And that's why your coffee spills when you do that. My coffee tries to continue on at a constant velocity, at the same speed and in a straight line, unless some force causes it to change direction or to change speed, some unbalanced force. What about if I set a ball on the table and it sits there nice and still? I think we can all agree that the velocity is constant then. But are there any forces acting on that ball? Absolutely. Gravity is obviously acting on that ball, and the table is supporting that ball. We can sort of see that the table is supporting that ball because if the table wasn't there, the ball would fall. So the table must be exerting some force on the ball. Professor Sheldon was kind enough to do a little demonstration for me here, and you can see he's got the sort of table set with the apple and all, the tablecloth, and when he pulls slowly, the objects move. But when he pulls quickly, all of the objects stay on the table. It's their inertia, which is related to their mass, that keeps them from moving. Their inertia makes it so that unless there's a force that acts upon them to make them move, an unbalanced force, they don't move. In the first example, when he pulled slowly, friction was able to move them, but when he pulled quickly, they essentially stayed in place. In this demonstration, Professor Sheldon is setting up 3 beakers topped by a metal pie plate and then 3 toilet paper rolls because, it's a high-class demonstration like that. And we're putting tennis balls on top of each of the rolls. In just a second, he's going to take a broom, bend it back, and then knock that pie plate out. What do you think is going to happen to the tennis balls when the pie plate is knocked out? Now we get a chance to watch the end of the demonstration. See it again? Excellent. So the balls fall straight down. No force acts on them in the X direction. The force of the sort of paper towel rolls or the toilet paper rolls that was holding them up is removed, so they fall down, but they don't move in X because there's no force exerted on them in X to make them move. We've used this term force a lot now, and hopefully you have a little bit of a sense of what it is, but one important idea to get discussed is the idea of whether a force is a vector or a scalar. And so we've talked about forces acting in X and Y, and we've talked about forces being up and down, to the left, to the right, and so what we really see is that force has to be a vector. It has both magnitude and direction, so it has to be a vector. The next question is, can a particle be subject to a force and not move? So if I have this block here, and I pull on it with a force of 10 newtons, and newtons are a unit of force, then if there are no other forces acting on this block, it's going to accelerate because it's subject to an unbalanced force. But if someone else is pulling on it from the other direction with a force of 10 newtons, that block will not move if it is at rest. And if it's already moving at a constant velocity, it will continue to move at that constant velocity. It will not accelerate, because while it is subject to a force, while there are two different forces exerted on it, those forces balance, they add up to zero. So the net force is zero, and so it doesn't move. Instead, we talk a little bit more about what a newton is. So it's a unit of force, and 1 newton equals 0.225 pounds. Again, you've almost certainly heard that pounds are a unit of weight, not a unit of mass. And by weight, we mean a force. So we can convert directly from newtons to pounds. We cannot convert directly from kilograms to pounds. And a newton has a value of 1 kilogram times meter divided by second squared. So if an object is not moving, if an object is at rest and it is staying at rest, then the net forces, the sum of all of the forces, has to equal to zero. Remember, I said force is a vector. So if you're doing the net force, you have to be adding the forces as vectors. You have to be taking into account their direction. So if the object is moving, but it's moving at a constant velocity, well, the same thing has to be true. The net force, the sum of all of the forces, has to equal zero, and we call that equilibrium. We can also write it that F net, so the sum of the forces, is the sum of all the forces. F net is a shorthand that we use. You'll also see sum of the forces, and they mean the same thing. They mean we added together all of the different forces acting on the body. You will also sometimes see F net x and F net y. That's just the sum of the forces in the x direction and the sum of the forces in the y direction. What we'll see is that if no net force is acting in x, then the body won't accelerate in x. That's kind of like projectile motion. If no net force is acting in y, the body won't accelerate in y. An object can be accelerating in x, but not in y. Okay, now's your chance to apply this a little bit. So a passenger on a bus claims that when the driver slammed on the brakes, a bag from the front of the bus flew back and hit her in the head. Is the passenger's claim true? And you can assume that the bus was traveling forward before the driver slammed on the brakes. A book is at rest on a table. We know that, and you're given 4 different options. The 5-kilogram book is sitting here on the table. It's not moving. As you saw in the last sort of conceptual question, we know that gravity is pulling down on this book. It doesn't matter if an object is sitting on something, being held up, being thrown. None of that makes the force of gravity go away. The force of gravity is always there. All we know is that the net force is equal to 0 because this book is not accelerating. It is staying at a constant velocity of 0 meters per second. So if we have this force that's downwards, for the net force to be 0, there must be an upwards force. That upwards force is called the normal force. When we say it is normal, we aren't talking about it being sort of ordinary. We're talking about it being perpendicular to the surface. So the normal force is a force that's exerted by a surface perpendicular to itself. So when an object is sitting on a table, the table exerts a normal force upwards. This is sometimes a little bit of a challenge for people because it's kind of hard to think of the fact that the amount of force the table exerts depends on the mass of the book. If I put a 10-kilogram book on the table instead of the 5-kilogram book, the force of gravity is actually bigger on the 10-kilogram book, and the table would need to exert a bigger force upwards to balance it. You do this subconsciously. If you hold something heavier, you start to exert a greater force upwards. So considering this normal force, if we have this horizontal surface here, we're going to talk about bags of money now because, well, why not talk about bags of money? It's kind of fun. We know that the force of gravity will be acting on this bag of money and will be acting downwards. And we know that there's a normal force that is perpendicular to the surface. Because this is a horizontal surface, that normal force just points straight up and gravity points straight down, and those two can add up to be 0. But what if the surface is tilted? The force of gravity still points straight down. Nothing changes that. Nothing makes the force of gravity go away as long as the object is on Earth. Obviously, the magnitude of the force of gravity changes if you're on the moon or something like that, but for all of our problems on Earth, force of gravity is going to be there and is going to have the same magnitude for this bag of money no matter where that bag of money is. The normal force might change a little bit though. So which of the following could represent the normal force from the ramp? Remember that the direction of the normal force is controlled by the direction of the surface. So the normal force has to be perpendicular to that surface because a normal force is always perpendicular. Well, now, when we look at this, hopefully thinking about what you've seen in terms of vector addition, you can tell that we can't add this vector and this vector and get 0. It's just impossible. And how big is the normal force? How do we start to figure that out? Well, what we're going to do first is we're going to break these vectors down so that we have sort of a new XY coordinate system. So what I want to have in the end is my normal force here, and I want to break the force of gravity into a direction, sort of a vector directly into the ramp and one along the ramp. We all know if this ramp was very smooth, like a playground slide, when I put the bag of money on, it would accelerate down the ramp. So we already kind of know that there's an unbalanced force in the direction down the ramp. We also know that this bag of money isn't levitating off the ramp. It's not going to jump off the ramp this way, and it's not going to crash through the ramp this way. So we actually know that the magnitude of this force into the ramp has got to equal to the magnitude of the normal force pointing out of the ramp. So now we're going to start to break down that gravity vector. So we have our ramp here with a slope of 25 degrees. We have the force of gravity, which is vertical. We're going to actually tilt the whole thing so that now our surface of the ramp is horizontal because we are going to let down the ramp be the x-axis. So our force of gravity now doesn't point straight down because we've rotated our whole view of the world. It's like we turned our heads sideways so that we're looking at the ramp as if it's horizontal. We could draw a line perpendicular to this new axis to create our triangle. If we did that, we would have a vector in this direction down the ramp like we wanted and one into the ramp like we wanted. But we need to figure out what angle to use. We know how we resolve vectors, but how do we figure out what angle to use? Well, we have a right triangle here from our original ramp. We know that this angle is 25 degrees, this angle is 90 degrees, and so this angle must be 65 degrees because 65 plus 25 equals 90. If we remember back to geometry, the sum of the angles in a triangle has to equal 180 degrees. So if we have 90 here, the sum of these two angles must be 90. The force of gravity is parallel to the original side of our ramp that was also vertical. If this line and this line are parallel and both intersect what is now our x-axis, the angle they make with that x-axis has to be the same. So this angle has to be 65 degrees. We have another right triangle here, so if this angle is 65 degrees, this angle has to be 25 degrees. If we look at this now, if we want to think about what this component of our vector is, it is opposite the 25 degrees. So we could say the force of gravity in the direction of the slope, going down the slope, has a magnitude of Fg sine of 25 degrees, which we see here. If sine gave us this component, then cosine would give us the component into the ramp. So the magnitude of gravity, or the magnitude of the component of the force of gravity that goes directly into the ramp, is Fg, the magnitude of the force of gravity, times the cosine of 25 degrees. We already said that the bag of money isn't levitating off our ramp, so the normal force must have the same magnitude as the force of gravity going into the ramp, which is Fg cosine of 25 degrees. This is a section that you may wind up watching once or twice just to get the hang of it. This is an issue that sometimes gives students a bit of trouble, and so you want to take some time and make sure you get it. So, looking at all of that, why does the bag slide down the ramp? Now that we know why the bag slides down the ramp, we're going to figure out why it slides down some ramps faster than others. So if I have my bag of money on my ramp, and we'll say I've just robbed a bank and need to get rid of my money quickly, so I'm sliding it out a window. And I have some options here. I have an option of a ramp with a slope of 10 degrees, in which case we could calculate that component that goes down the ramp would have a magnitude of Fg times the sine of 10 degrees. We would do that by breaking down this vector that is the force of gravity. We know that the bag is not accelerating in this line perpendicular to the ramp, so we know the force of gravity into the ramp and the normal force are going to have the same magnitude, but they point in opposite directions. And the bag is going to slide down the ramp because of this component of gravity that's in the down the ramp direction, which has a magnitude of Fg times the sine of 10 degrees. If I have a 45 degree ramp, it's going to have a force pointing down the ramp of Fg times the sine of 45 degrees. If I have the same bag of money, that Fg, that force of gravity on the bag, is going to be the same regardless of the ramp. So for which of the ramps would the net force have the greatest magnitude? And if the net force is the greatest magnitude, as we'll see in a bit, that means that it would slide down the ramp the fastest.